So the whole reason that I wanted to get you this, and that I wanted to remind you that we were in this inertial reference frame where we get to use this idea here, is in particular, if the net force is time dependent and the mass is not time dependent. This is kind of a strange thing, but we're imagining our automobile's mass not to change from its 5,000 kilogram value. So this is stuck in time. But Newton's second law is written this way. If there is a time-dependent net force, then there is a time-dependent acceleration. And here is our time-dependent acceleration, but that's not what I want to use this for. I want to use this because I would like to say, what is the net force as a function of time? Well, it's m times the acceleration as a function of time, which is right here. So in this particular uniform circular motion case, this will be mr omega squared minus cosine omega t I hat minus sine omega t j hat, like this. And the reason I want this is so that I can calculate an interesting impulse. I want to study the problem of how much impulse is delivered to a car which is in uniform circular motion. So here's our car, and it's feeling a net force right here. It is a function of time, and if I know the net force as a function of time, I can calculate what's referred to as the impulse by the net force. This is how you calculate it right here. You could say this is the definition of the impulse by the net force. The impulse momentum theorem what it says is, if there is an impulse on an object, the change in the momentum of that object is equal to the amount of impulse that was done to it by the net force on it. Yeah, so this is what the impulse momentum theorem says. Okay, good. So I'm going to go ahead and write out this thing on, maybe I'll put it here, with this function of time sitting here, and we can look at it for a second. So J net equals, so it's the integral from t1 to t2. So we have to specify times that are interesting. For us, the times that are interesting are 0 and 20 seconds later. So we'll put a 0 and a 20 seconds in a little while. But let's put in F net. It's mr omega squared times minus, I'm looking at the right thing, cosine omega t. Check it out, there's a vector in there, minus sine omega t j hat. So omega squared, the vector business, but then don't forget the little dt. This is a small amount of time to multiply on the integrand. Okay, so I'm going to rewrite this though as the following. I'm going to split it up into two parts. I'm going to say that there is an x direction part and a y direction part. So I'm going to say that there is a net impulse all in the x direction that multiplies the I hat, there's the same I hat, plus a net impulse in the y direction that multiplies the j hat, where the net impulse in the x direction is equal to, I just have to look at everything in the x direction except for the I hat. So it is mr omega squared integral t1 to t2. There is this minus sign. Let me pull it out. So there's a minus out in front. Let me parenthetically put it all together. So minus mr omega squared integral t1 to t2 of cosine omega t. But don't forget that there is this other common factor that's written after the parentheses. This common factor dt sets us up nice for this integral. And because the I hat is outside of this definition of this j net x, I do not put the I hat anywhere in here. The I hat is accounted for outside. So this is all of something I'm going to refer to as the x direction impulse delivered by the net force, which is a vector, between the times t1 and t2. And there is also a net impulse in the y direction. I'll just write it down. It's minus mr omega squared integral t1 to t2 of sine omega t, like this, dt. All right, so I've got this. I'm just kind of exploring, but if I want to go back and look, I am setting myself up to be able to calculate this thing, this impulse delivered to the car in uniform circular motion. I have just written down how to do it. This is the impulse delivered to the car between, honestly, any two times during the circular motion in the x direction, and this is the y direction part. Okay, let me think a second. Oh yeah, so here's where we're going to go next. Let's look back at what's been going on. There's been, honestly, kind of a lot of math. There is some physical context, and we can put numbers and units and all kinds of stuff. But if you sit back and look at just like, you know, if you gave this to a person who wasn't taking physics yet, they'd say, holy crap, look at all that mathematics. And the thing is we aren't, I mean, we are doing a bunch of math, but we're not in a math class, right? We are doing physics. So let's sit back and let's be physicists for a while. So let's go and inspect what's going on. This little car is in uniform circular motion, and when there is uniform circular motion, there are, the thing that causes that is centripetal force, right? So there's centripetal force. And the idea is centripetal force must be the net force. That is, there aren't any other forces that will cause this to not be pure centripetal motion, is the idea. With some caveats about the meanings of the word centripetal. But anyways, anyhow, so there is this center-pointed, right, centripetal force. And this centripetal force, as the car continues around the circle, that centripetal force, its direction is updating. And then as soon as the car reaches 20 seconds and straightens the steering wheel back out, that centripetal force vanishes. And when the centripetal force vanishes, the car doesn't have a net force, or it has net force actually equal to 0. So its velocity can no longer change. It's not accelerating anymore, and all it can do is the inertial thing of going straight, right? Inertia means that if the net force is 0, then the conditions of the car's momentum do not change in time, right? Okay, so let's be physicists. What should, or actually, what do we see? So what we see, we're supposed to have the bird's eye view. You don't have to have the bird's eye view all the time, but this is a particularly nice place to stand because you get to use inertia and inertial laws, Newton's laws of motion, on which actually the momentum impulse theorem depends. So what do we see? We see a momentum of the car. The car comes in with an initial momentum upwards at t1. So p1 is this upwards momentum. So this is the incoming momentum. And then impulse happens for 20 seconds, or over 20 seconds, impulse happens. So some process occurs, and there is, at the end of it, an outgoing momentum that is this way instead. So incoming momentum is like the initial state. Impulse gets to occur for 20 seconds, and the outgoing state or the outgoing situation is the momentum is different. It is purely sideways towards the left. Before it was purely upwards with no sideways momentum. But let's continue to be physicists. Uniform circular motion means that the speed is constant. And if the speed is constant and also the mass is constant, that means that the momentum, there's something constant about the momentum. What's constant is the magnitude. So the incoming momentum is of the same size as the outgoing momentum, but they are definitely not in the same direction. So P1 and P2 are not in the same direction, so they don't have the same vector value, but they do have the same magnitude. We're just being physicists. What we're doing is we are thinking about what uniform circular motion means. So I can go and I can actually say what the magnitude of the momentum is. It's m times whatever the uniform circular motion speed is. And that uniform circular motion speed, we calculated over here, this constant uniform circular motion speed, is this crazy stuff with the, the pi's and all this stuff with the meters, size of r and things like that. But the other place that that uniform circular motion speed is at is actually right here. This is the uniform circular motion speed. If I go and ask what is the magnitude of v, it turns out that if you check the magnitude of v, it's the result of taking the square root of the dot product, and this will, if you use this v of t that we have for circular motion, uniform circular motion, when you do the square root of the v dot v, this is what's meant by the magnitude of a vector. The square root of the dot product of a vector with itself is the magnitude of the vector. And it turns out that even though this v of t has time dependence all up in it, only the direction, it turns out, is time dependent. When you do this dot product, what you're going to get is r omega with no time dependence. If you have no time dependence, then with respect to time there is no time derivative, right, or the derivative is 0, which means that this does not vary in time, is what it means. So here we go, P1, which is m times v. This is the value of the magnitude of the momentum the whole time the car is in here. So so we're continuing to be physicists. So like